Okay, it looks like that is visible. So I'll go ahead and get going. Okay, well, thanks very much for the invitation to speak here at ASQC. I hope to catch a little bit more of the workshop as the week goes on. It's been kind of a crazy couple of days. But yeah, anyway, I'm very happy to talk about this recent work. This is joint work with Renaud Vimar at Saclay and John van de Wetering, who's in Oxford, a postdoc in Oxford with me, but also based at Radboud University in the Netherlands. Okay, so I'm going to take a bit of a roundabout route to talking about simulation and talk about optimization of quantum circuits first, and then I'll talk about why that matters for simulating quantum circuits. Okay, so as I guess most of you will know, quantum circuits are sort of an assembly language of quantum computation built out of gates. And gates cause noise and take time. So smaller, shallower circuits, so doing the same unitary with less gates equals a happier quantum computer. Okay, so there's a lot of interest in trying to optimize quantum circuits in various kinds of ways. Okay, and this is a kind of imaginary, old-fashioned way you could think about optimizing quantum circuits, which is really just by kind of peephole optimization. So you can think about some sort of gate identities which would apply to a circuit like this one. So for instance, if I have a pair of Hadamard gates, I could push them through a C0 gate and the C0 flips around. And then if I have a pair of C0 gates like this, well, then they cancel out with each other. And as a result, I get a smaller circuit. So in particular, I didn't need to calculate this unitary to try to synthesize something smaller. I just used some rewriting to do some optimization. And you can get some mileage with this. The problem is you don't really know where to stop, right? So you can come up with a few circuit identities and then a few more, and then more and more and more. And you know, there's no real structure to these things. You kind of you just kind of come up with these things as you need them, I would say. So the kind of, I guess, main crux of what I would call the Oxford approach, or a kind of approach that grew out of Oxford, but now a lot of groups are working on for solving these kinds of problems, is actually not to look at gates, but to take gates and cut them up into something that's more primitive. So this kind of diagram you get from a quantum circuit is called a ZX diagram. And these things which are more primitive, so these red and green dots, or these dark and light dots, are called spiders. So a spider is really just a type of linear map. It can have any number of input wires and any number of output wires. And this is always a 2 to the m by 2 to the n matrix, and it's got a 1 way up here in the top left, and it's got an e to the I alpha way here in the bottom right. So they're always parameterized by an angle alpha. So if you think about the one that has just a single wire in and out, this is just a Z phase gate. But if it has lots of legs, then it's this rank 2 matrix, which can be arbitrarily large. So most of these are actually singular. Now, as soon as we have green spiders, we have red spiders just by a change of basis. So if I conjugate the whole thing by Hadamards, then I get the red spider. And using these two things, I can actually build any quantum circuit. So I have a language which is universal for quantum computing. Okay, so one of the immediate benefits you get from working with these rather than gates is the kind of flexibility of spiders. So I can think of a ZX diagram as something that's more like a tensor network, or really just an undirected graph, because I can just deform this thing at will. And as long as I have the same nodes and they're connected in the same way, then this describes the same linear. And they also satisfy a collection of rewrite rules, sort of equations between diagrams called the ZX calculus. So these 1, 2, 3, 4, 5, 6, 7, 8 equations actually imply all of those, pages and pages and pages of gate rules that you could come up with. Okay, so going back to this sort of toy example, if I cut my gates up into spiders and I start applying these rules, well, one of the rules is if I have spiders of the same color, I can fuse them together and they become single dots. And then I can sort of copy dots of one color through dots of the other color. I can do some more fusion and apply some other rules, and you see that actually I get a circuit that's much simpler at the end by applying these ZX rules. Okay, so that was, as I said, just a little toy example. It had about 30 spiders in it. In fact, for doing real kind of interesting optimization problems, and actually even problems which are interesting on, say, NISC, like small hardware, as soon as you're talking about something like 20 qubits, depth 20 or something, then you're talking about hundreds or even thousands of gates. So you really need some kind of automated tools to do this kind of simplification. Okay, so we have such a tool. So one of them is called PhysiX. It's like pronounced like physics without the H in it. It's a Python library for doing circuit optimization and simulation in the ZX calculus. So this is an open source tool. You can get it on GitHub. There's lots of documentation. It's kind of fun if you like hacking around in Python, just to get this thing and sort of run through some notebooks and play around with ZX diagrams and code. So this is our kind of small, fun hacking around ZX calculus library. For doing some serious computation, there's also a port of this to Rust. So Rust is a kind of a systems programming language for writing very fast programs, called QuizX. This is a large-scale circuit optimization and classical simulation tool for the ZX calculus, which you can also find on GitHub. So I'll show a little bit of QuizX later. Okay, so the main idea in this paradigm is that I have some circuit which I can read almost immediately as a ZX diagram. I've got a kind of a one-to-one translation between the gates in my circuit and these kind of little collections of spiders. Okay, so this thing is like a C0 gate, and these things are phase gates, and so on. So I read this thing as a circuit, and then I do some simplification, and I get down to some minimal thing, where all that's left is really the kind of essence of that map. And by that, I kind of mean what's left is the non-Clifford structure. Okay, so this was actually a big Clifford+T circuit, which had, let's see, I can count them. It had 1, 2, 3, 4 T gates in here somewhere, which you can see as pi/4 phases. And by the time I do a simplification with ZX calculus, it kind of eats all that non-Clifford structure, and it kind of remembers where the T gates were and how they're causally related to each other. So this is a little bit like how in measurement-based quantum computing, you can kind of do all the Clifford stuff at once, and actually the important thing is where your non-Clifford measurements were and how they're related to each other. Okay, so we call this little thing the skeleton. And then once you have this skeleton, you can use it for a number of things. Actually, for the simulation, you kind of use it directly. But if you're wanting to do circuit optimization, you might try to extract now a smaller circuit from this. So you can kind of work from one side and do a kind of a technique, which in some sense is like Gaussian elimination, where you actually can resynthesize a Clifford+T circuit from a skeleton. Yeah, so once we're in this kind of shape, again, I can kind of read the gates back off of it. Okay, so a few years back, we applied this to doing T-count reduction. So that's really just reducing the number of T gates in a circuit, which you can always see them as these odd multiples of pi/4 angles in these ZX diagrams. And I guess probably many people are aware that T gates are kind of an interesting thing to try to reduce for fault-tolerant quantum computing, because they're quite complicated to implement. Say in the surface code, you need to do magic state distillation or something like that. So less T gates is always a win. Okay, so applying this kind of simplify and extract technique, you can actually reduce the T-gates, because in the process of computing the skeleton, T-gates will either meet each other and become non-T-like phases, or they will actually cancel out. So actually in this picture, if you're not so quick at counting, there's 6 fewer T-gates in this bottom one than there are in the top. Okay, so we tried this and it worked pretty well, compared to the sort of the state of the art in ancilla-free T-count reduction. So here we were doing it without ancillas. You can actually do a lot better if you introduce some ancilla qubits into this. But for this ancilla-free case, about 72% of some benchmarks we tried were matching the state of the art a few years ago. And some of them were doing a bit better than what people have done so far. At virtually the same time, Zhang and Chin came up with another technique based on what people are now calling Pauli gadgets, which got the exact same numbers. So somehow this kind of simplification procedure is a version of this kind of method of using Pauli gadgets, or Pauli exponentials, if you know about these things. Later that year, some people around the Oxford group came up with a new ZX method, which did a little bit better, and then I think some other people have done better, and the T wars continue, let's say. But yeah, so why was I telling you about circuit optimization and about T count? You know, who cares about T count? You know, this is very important for long-term fault-tolerant quantum computing. But if you're a skeptic and you think that this is 10 or 20 years away, then why does T count matter? Well, one case where it is actually becoming very important is doing classical simulation of certain kinds of quantum circuits, of doing Clifford+T circuits, which don't actually have that many T gates. You can classically simulate them. Okay, so classical simulation is hard for quantum circuits. We hope. Otherwise, we're kind of wasting our time. All the known algorithms are exponentially hard in some measure of hardness of the circuit, right? But that kind of measure of hardness varies depending on the technique you're using to simulate a circuit. So that can be number of qubits. So that's like state vector simulation. Really, just if I have not very many qubits, I can just simulate naively. If I'm simulating using tensor networks, then it's the tree width that's really important, or maybe the fidelity that I want. But a very interesting family of techniques are the hardness of a circuit really has to do with the T count. And these kinds of techniques are what I would generally call stabilizer decomposition techniques. So decomposing based on the stabilizer rank or the stabilizer extent. The stabilizer, I'll only talk about stabilizer rank decompositions. Stabilizer rank decompositions simulate a hard circuit by summing over simulations of lots of easy circuits. So basically, if I'm preparing some non-stabilizer state, then I write this as a sum of stabilizer states, and I simulate each of those, and I sort of sum up the results. Okay, so the stabilizer rank of an arbitrary state is the least capital N, so this N could be very large. It's the least N, such that psi is written as a sum up to N of some stabilizer states. Okay, so if it's a sum of not very many stabilizer states, this thing is actually going to be pretty easy to simulate. And in fact, one thing you can see immediately from writing it in this form is that amplitudes can be computed in n times polynomial time, because I can use Gottesman-Knill to compute the amplitudes for each of these terms, and then I just sort of sum them all up at linearity. Okay, so coming up with good stabilizer decompositions actually gives me fast classical simulations. Now, this is hard to compute in general. It's almost too much to hope for to get exact optimal stabilizer decompositions. But there are some upper bounds based on kind of computable techniques for doing stabilizer decompositions. And I think all of these, all of them, the ones that I know about, do something like a magic state decomposition. So you write a circuit, a Clifford+T circuit is actually a Clifford circuit, which has some T magic states plugged into the bottom, and maybe it has some outputs being post-selected on 0 or something like that. So I write this thing as a Clifford circuit applied to some T magic states and maybe some 0 states, and then I just decompose as a sum. Now, naively, I just decomposed these magic states into 2 stabilizer states. This one and that one, right? These are basis states. They're actually stabilizer states. And if I do this, I'll get 2 to the T terms, stabilizer terms. So, if I only have 4 T gates, this is a perfectly sensible way to simulate even a 100 qubit Clifford+T circuit. You can actually do a bit better than this by taking chunks of T gates at a time. So the first one of these I saw was due to Bracke, Smith, and Smolin, who decomposed 6 T magic states. So this H thing is basically this T thing. I think there's maybe some kind of incidental difference, so maybe scaling factor or something. So you can decompose 6 of these things, or a tensor product of 6 of these things, as this fairly complicated looking expression where each of these things is a stabilizer state. And now, rather than getting 2 to the T terms, I actually get, well, there's 7 terms here, but I decompose these things 6 at a time. So I get 7 to the T over 6 terms. So that's about 2 to the 0.468 terms. So you do a bit better, and actually the state of the art is this number is, I think, 0.39 or so. So it's kind of coming up with better ways to do this. You can get this kind of prefactor on T to be smaller and smaller, which is quite useful. Okay, so I'm going to talk about what this looks like in ZX language. Okay, and actually this translation is not very complicated. It's really just translating the notation at this point. So from kind of textbook Nielsen and Chuang notation to ZX notation. Okay, so Clifford+T circuits translate this way. So my C0 gates look like that, S, H, T gates. This is what a basis state looks like. So if it's a 0, then I have a dot with no pi on it. And if it's a 1, it's a dot with a pi on it. And similarly, this is what a bra looks like. Okay, so I can write single amplitudes this way, as I have my gate decomposition, which I can write as a ZX diagram, and then I can just plug in a bunch of 0 states on this side. And then if I'm interested in the amplitude associated to a measurement outcome, I can plug in those bras on this side, right? And this is a ZX diagram which has no inputs, no outputs. If I can simplify this all the way, it becomes just a scalar, okay? And in that case, you win, because that scalar just is the amplitude. Okay, so this is a way that actually simplifying diagrams is doing some kind of simulation, and we take advantage of that. So calculating amplitudes is actually just kind of is just part of the story, really. It's a subroutine in classical simulation, and then you may want to consume that in some other more elaborate way of actually being able to, say, sample your probability distribution of measurement outcomes. The simplest thing you can do is, well, simplest to conceptually simplest, but maybe work-wise the hardest, but it is in fact what we end up doing, is strong simulation. So to be able to calculate probabilities or marginal probabilities, well, here's just let's say some marginal probability on some n-bit string. Okay, that's just summing over some bits that I'm not interested to get the first k bits, right? So this probability I can expand using the Born rule. And then since I'm summing over this xk plus 1 to xn, these basis states, that just becomes a identity matrix here, tensored with some basis states, right? So here here's kind of how you calculate marginal probabilities with the Born rule. You can probably find this in a textbook somewhere. And this is just what it looks like in the ZX calculus. So if I'm interested in, say, the probability of only the first outcome being 0 or 1, I just plug that in here, and then I connect everything up with a wire. The reason that this can take a lot longer to simulate is actually, you see my circuit got doubled here. So here's one copy of my circuit, and here's the adjoint of the circuit, which is basically another copy of it. But it will turn out in the approach I'm going to talk about, this is not that bad to end up doing this kind of doubling. Okay, so that was really just about, how do I calculate amplitudes and probabilities using ZX, right? And I guess I should mention that as soon as I can calculate marginal probabilities, I can sample this distribution. This is like saying that or 1, and then calculate the second marginal, and so on until I get a full sample, which we'll see in a minute. Okay, so stabilizer decompositions in ZX. We really just take these decompositions, which you can find in papers and some that we've sort of come up with on our own, and translate them into ZX calculus notation. So now, rather than seeing 6 T magic states decomposed as some stuff, we see that we have 6 pi/4 spiders, which decompose as some stuff. And you notice this is basically the graphical version of the BSS, the Bragi-Smith-Smolin decomposition. Here we have 6 T-like things, and none of these things are T-like. So that's to say that all the angles here do not contain odd multiples of pi/4. So all of these things are efficient to simulate using ZX-based techniques or other kinds of techniques. They're all stabilizer states. Okay, and another way you can see this is these are basis states, and these are basically GHZ states, and these are just graph states with some local Cliffords on them. Okay, so here's the procedure now that we've translated everything into ZX notation. So first of all, we take our circuit and we read it off and say we want an amplitude, then we just draw the picture of the amplitude we want. Then we simplify that diagram as much as possible using the kinds of techniques we came up with for circuit optimization. And then once we're stuck, it means that we have some pi/4 spiders in there. So we replace up to 6 pi/4 spiders with 7 terms. Okay, so if there's less than 6, we can sort of do smaller decompositions and so on. But now we have more non-Clifford stuff. So for each of these terms, we just go to 1 and repeat. Okay, so we decompose, simplify, and so on and so forth. Okay, and this terminates when everything is simplified. Okay, and fully simplifying something really just gives you a scalar. So I sum these up and I get an amplitude, or if I'm doing calculating marginal probabilities or something, I get a probability. Okay, so suppose here I'm just kind of drawing a schematic of what I had on the previous slide. Suppose I have a ZX diagram or a circuit with 33 T-gates in it, and I have kind of one instance of hardness 33. Well, I split that into 7 instances of hardness 27, and I split each of those, hardness 21, and so on. And this is how the kind of the standard approach would work, is you just decompose all the way, and then you simulate once everything is Clifford. And this produces, for instance, with the BSS decomposition, to the 0.468 terms. But then if you start interleaving this with simplification, then some of these T-gates will cancel out. And in fact, this can make a big difference, right? So in fact, if one of these branches gets to 0 T-gates, you kind of killed off this whole sort of part of the tree. And this can give you much, much fewer terms in your simulation. Okay, so we can try to quantify how much better this does. And I can give you a theoretical answer, which is which is okay, but doesn't exactly capture the imagination. But then also the way this works in practice is, I think, pretty surprising. So in the worst case is when no t-like phases are actually killed during simplification. So after doing a polynomial amount of work, which we'll just kind of ignore because we're going to have exponential stuff in the big O anyway. After doing a polynomial amount of simplification, we get to a diagram which is of size order of t for t, how many t gates we started with. Okay, so we kind of kill off all the non-Clifford stuff, and we're just left with the skeleton, which has basically as many nodes as we had t gates. After doing a decomposition, doing further simplification only takes a constant number of more rewrite rules. Okay, and each of these take order t squared. So since there are a maximum of 2 to the alpha t diagrams in the sum, the total cost is 2 to the alpha t t squared. Okay, so you'll notice that there's a quadratic dependence on t here. So if you compare this to an approach which does all of your decomposition first, and then does Gottesman-Knill at the end, which is basically a cubic thing, basically a cubic thing in the number of t gates, then this is 2 to the alpha t cubed. So we actually get a bit of an advantage kind of in the asymptotics. And the reason for that is that the ZX simplification actually lets us partially simulate, I would say, these diagrams by simplifying them. So we can kind of eliminate as much of this Clifford stuff as possible before we decompose. So it stops us repeating ourselves, and this gives us a bit of an advantage. So I like to think of this as something like eager evaluation or partial evaluation, which is something like classical compilers do. They try to evaluate your code as much as possible even before it gets an input, so that as soon as it gets an input, it does what it was going to do faster. Okay, so this is just the worst case. In practice, many t gates can cancel out. Okay, so I'll just look at an example and give a little demo. So here's a hidden shift circuit. So it's just a particular circuit for solving the hidden shift problem with 50 qubits and 280 t gates, which actually came from CCZ gates, which we decomposed as t gates. So doing the Ravi-Smith-Smolin decomposition, this will take 10 to the 39 stabilizer terms, and even the state of the art will take 10 to the 33 terms to compute an amplitude, which is not practical because assuming 1 nanosecond per term, this will take way longer than the age of the universe. Okay, so let's see it in Quizzix. Let me just bring this up here. So here it's actually computing all of these successive marginals. So it's computing the first marginal, and then probabilistically going to the next one and computing the next one, so on and so forth. And you'll notice each of these actually happens really quickly. And in many of these cases, it was able to get rid of all of the t gates straight away using the simplifier. And then occasionally it hits kind of a hard case. In this case, actually, after the first hit, it had 24 t gates left, and then it does this kind of decomposition thing. Maybe I should make that a little bit larger. And you'll see that we actually got a full sample from this circuit, which was correct. So here was what the shift was that we put into the thing, and here's what our simulator said. And we did it in 7 seconds. Okay, so much less than the age of the universe. Okay, so I mean that was just one example. We tried this on random circuits. Well, it's a heuristic algorithm. It doesn't always work. And our kind of strategy, we decided, was to let the thing run for 5 minutes, and then if it didn't give me a good answer, and yeah.
Alex, I'm sorry, we couldn't see the demo that you just did. Is it possible to just give it another try?
Sure. Oh, I see. It's not. It's hang on. Let's.
Oh, now we saw it. Was that the plot that?
Oh, Oh, I think I was sharing a single window.
Yeah.
Ah, okay. Let me share. Share. Okay. Okay. Now do you see a terminal window?
Looks good.
Yeah.
Okay. All right. So slightly steals my thunder, but so this takes the age of the universe. Let me run the thing. Okay. So this is a hidden shift instance with 50 qubits, 20 CCZ gates, which translates into these 280 T gates, and then a random seed of 2. And here it goes. So that's just pulling outcomes for each of these successive qubits. And you'll notice that here, in many cases, it was able to get rid of all the T gates straight away. In some cases, it had a slightly harder challenge, but it got rid of a lot of T gates, and then it did this kind of decompose and simplify thing. And so to get qubit 5, it actually took 160 milliseconds rather than a few microseconds. And all in all, we were able to simulate this time in about 8 seconds, this hidden shift circuit, which of course is much better than 10 to the 33 nanoseconds. Okay, so that was one example, and yeah, it's a heuristic. If I chose a different seed, your results will vary, of course. We tried this on a bunch of random circuits, and decided to basically let the thing run for 5 minutes, and if it didn't return an answer, we'll just call it a failure. Okay, so this is the percent that were successful versus the T count on just random circuits. So not really structured. Actually, what we were doing is random Pauli exponentials up to a certain depth of T. And you see that for 10, 20, 30, up to almost 50 for these 100 qubit circuits, but these are still relatively sparse circuits. We were 100% successful. And then as these random circuits start to get deeper and deeper, this sort of drops off, and you start to sort of feel the sharp edge of this exponential behavior, right? You wouldn't expect random circuits to be, efficiently classically simulable, but the big sizes. Then if you look at the ones that we did successfully simulate, and the kind of reduction between the number of terms that we ended up needing to sum and the naive BSS number of terms, you see we have an improvement of up to kind of 15 orders of magnitude. This becomes less if you take the initial circuit and you actually just hit that thing straight away with our simplifier. That actually gets rid of a lot of T gates. So one of the lessons of this thing is of this whole approach is that you should always do optimization before you try to simulate using any method. But you can see for the random circuits, we do get improvements of up to kind of 30 times better or something if we still do this interleaved approach rather than some other kind of simulation. The hidden shift circuits, which is what I showed you the demo of, so now these are structured circuits, not random circuits, performed much better. So here's the T counts down here. And again, we initially started 100% successful, but here we're starting at a T count of 70. And you see that we're actually managing to simulate some circuits, even, about 8% of them up to a T count of 1400. Okay, so here we're simulating a circuit with 50 qubits and 1400 T gates, which is about 20 times as big as this approach has ever been kind of applied to circuits before. And yeah, this of course gets these kind of big reduction factors. Now we're talking something like 400 orders of magnitude. To the extent that means something. I mean, we're comparing some exponential function to something that was an efficient heuristic. And again, the results are a bit more modest if we compare doing an initial round of simplification and then simplifying versus our approach. but still we get sometimes improvements of 8 or 9 orders of magnitude. So pretty significant there. Okay, so in conclusion, using ZX, we can greatly speed up stabilizer rank simulations, it seems. And in fact, anytime you're doing some kind of simulation, which is depending on certain kinds of gates, certain kinds of structure, you should really be doing optimization to speed that up. This works especially well for structured circuits. So something I didn't talk about is now we have a sequel to, I mostly talked about the first paper, but there's now a sequel paper out where we're really using the ZX structure in kind of a crucial way. So everything else I showed you, you could probably plug in your favorite circuit optimizer there and get kind of similar stuff happening. But in the sequel paper, we're actually looking for more interesting kinds of substructures, which are really diagrammatic. So rather than just tensor products of T-gates, we're actually replacing interesting kinds of subgraphs. And this does even better. So I'll put up a link to that paper in the next slide. And the kinds of things we're thinking about now are using more diagram optimizations. So one thing that's really fun about this approach is that you don't have to worry about trying to extract the circuit at the end. So this optimization thing, you have to be careful about what kinds of ZX rules you apply, because you have to be able to extract a circuit out at the end. Here you can just kind of throw the kitchen sink at it. And if you make progress, then that's good, because you're really just trying to totally simplify this diagram. So we're looking at other ways to simplify diagrams, which we know can kind of break our normal circuit optimizer for doing classical simulation. So finding heuristics for picking good places to do the decomposition. So this is also kind of related to tensor network techniques, where you try to pick kind of thin places in your tensor network to break it apart. If we can find kind of weak points with T-gates to do the decompositions there, I think we can get some benefit. Also doing other kinds of more elaborate things like approximate simulations, weak simulations. So this was all strong simulation stuff, which you would expect is harder than weak simulation. And also trying to apply some ideas around stabilizer extent, which is a different kind of measure of how close you are to stabilizer states as a sum, but now in a kind of a continuous measure rather than just counting the number of terms. So we're thinking about trying to ZXify this. Yeah, I think that's about it. So thanks for listening. Here's the 2 main papers where we describe this stuff. Yeah, here's some sort of more background papers related to that. So thanks very much. I'm happy to take any questions.
So the owl is disconnected. Is this okay or not good? Yeah. Good. Yeah, we can turn it around. So let's do a. Can you hear? Can you hear us now?
Yes.
Yeah.
Oh, that is fantastic. We have a solution. So we can begin with a question session. All right, the floor is open for questions.
Shall I just call on people or let the chair do so? I'm happy to.
Are there questions in the chat?
Yeah.
Good. Maybe Michael, you read them from, top to bottom.
Or like David.
They're raised from all.
Oh, okay. Michael, please moderate.
Okay, we'll start with David Gossett. Do you have a question?
Okay, thanks. Yeah, and thanks a lot for a really nice talk, Alex. So I was particularly fascinated by this, your heuristic algorithm for the hidden shift. And, do you think that you've identified a kind of structure in those circuits that, allows for efficient simulation and that we have not understood, like from a theory perspective?
So I think this particular family of hidden shift instances is simulable. Now that this, I don't want to say something wrong because this was about a year ago that I was in the weeds here, but I think this is a classically simulable, or at least this problem has a polynomial solution. I mean, the thing that's kind of interesting is that we're not, the simulation that we're doing isn't putting any knowledge about hidden shift into how we're doing the simulation. We're really just applying our kind of generic technique of getting rid of T-gates. A kind of a thing that seems to happen there is that, well, because we're computing marginals, we have this kind of doubled structure. So we have the circuit and it's sitting with its adjoint, and a lot of common wires are kind of plugged together. Particularly when you're computing kind of big marginals. So when you're only looking at a few qubits, so you get a lot of gates canceling across the two sides of the thing. And it seems with the hidden shift circuits that even when there's some obstruction there, a lot of the structure just cancels out. So if you'll notice in most of those cases, our simplifier actually gets rid of all of the T-gates.
Yeah.
Which is pretty surprising, I would say, and I still think we really need to get some better kind of traces of this thing to see what's actually going on, why our simplifier is doing so well on these kinds of circuits. You certainly see with the random circuits this behavior falls off pretty quickly as these things start to get denser.
Thanks.
Okay, Aslan, you have a question? Aslan, do you want to unmute yourself? Oh, you're muted. Okay, maybe we'll come back to Aslan. Josh, do you have a question?
Yeah, hi. Thanks for the really interesting talk. I guess I have two related questions, which are both about the complexity here. So I'm wondering what's known about, for example, complexity of computing stabilizer rank, or for example, of sort of the computational complexity in the worst case of the difficulty of finding, I don't know exactly what the minimum ZX circuit, I guess what I'm wondering is there some, formal complexity theoretic reason to expect that we can't get, beyond just sort of good heuristics, or is that, what's known there?
I think, again, I don't want to say something silly here, and maybe David knows some of this stuff too, but as far as I know, there's no exponential lower bounds on how hard it is to compute the optimal stabilizer decompositions, and I think this would imply some pretty surprising stuff, like being able to separate BQP from P or something like this. If we did have that kind of.
Yeah, I think you could say even more that if like M magic states could be decomposed using a polynomial number of stabilizer states, then you could solve sharp P complete problems in polynomial time classically. But yeah, there's no, as you said, there's no unconditional lower bound on the stabilizer rank, even though that problem has nothing to do with complexity.
Yeah. So this is certainly pretty catastrophic for quantum computing if this would be polynomial, or for complexity theory in general, let's say. yeah, for essentially the same reason that those same things apply to ZX diagrams. We actually, so one thing that I was kind of nerding out about at the end, I was talking about how this is a really interesting problem because you don't have to worry about extracting a circuit from a ZX diagram at the end. We have a paper in iCalc this year where we're showing that if you have just a ZX diagram and you don't know anything about it except that it's unitary, then this is actually number P hard to extract a circuit from it. So you actually have to be quite careful about how you apply these rewrites if you want to use it for circuit optimization. Otherwise, there's just no hope of getting a circuit back out of these diagrams again.
Good. Sergey?
Hi, thanks for the talk. Have you tried benchmarking your ideas on 2D circuits? Because the reason I'm asking, because there's more flexibility when it comes to tensor network contraction when you work with 2D. You can track from this side, from the other side, and you can exploit all kinds of interesting holes in the gates when they're acting, when they're not acting. So have you tried applying your toolkit to this sort of 2D type circuits?
Not deeply. So I mean, when the supremacy results came out, we spent a long time kind of scratching our heads and looking at the circuits that they were using, the random circuits they were using, which was on a 2D architecture, which also had this kind of intriguing kind of bottleneck spot because one of the qubits was dead in the original experiments or something like this. So there was this spot where things were a bit narrow. And we spent a while thinking about, can you find interesting patterns of T gates along, or in this case, just of arbitrary phase gates along these kinds of weak spots, and try to sort of break this thing apart, and maybe even try kind of hybrid approaches where you're doing some stabilizer decomposition, some tensor network stuff. But we haven't gone too deeply into that yet.
Good. Thank you. Can we give Aslan? Oh, sorry. Is there a follow-up question here from Sergey?
No, it's okay. It's all good. Yeah, thanks.
Fantastic. So maybe we can give Aslan another try. Aslan, you were muted first time around. Can you ask your question again?
Hi, sorry. My computer runs out of battery before I just reboot into that. Okay. So my question is, during your BSS decomposition, have you observed that your ZX diagrams disconnected? Sorry, disconnected into smaller graph states, smaller ZX diagrams?
That's actually something that we're looking at now. So I mean, I guess the short answer is no. I mean, we weren't checking. We weren't watching these things to observe if they were disconnecting. But something, there's a master's student, Julian Kodzi, is doing a project this year and looking at things like this, like disconnecting into individual components, and then kind of taking advantage of that. And then maybe also trying to choose your T gates such that this happens.
That's I'm asking this because I was thinking, like, if we want to do circuit extraction, it will be certainly better if the graph state disconnects into little pieces. Yeah. Thank you.
If I may add on to this, so Aslan did work precisely on this disconnection problem in research, undergraduate research work that he did here. So maybe there's more to talk about, and Alex, maybe you can connect Aslan to your student.
Yeah. So you studied what when graph states disconnect?
Yeah, but I haven't applied BSS decomposition. It's just like during the local computation process and removing all the other qubits measured in that basis. That sort of process seems sometimes for random circuits that the whole graph state disconnects into little pieces.
Yeah, we should definitely talk more about that because our simplifier is actually very its sort of main subroutine is local complementation. Because these ZX diagrams are also, if you squint right, they're basically just graph states. And local complementation is our main kind of way that you use to start deleting nodes.
Thank you.
Good. Michael, if I see it right, there's no questions here on Zoom.
Yeah.
So maybe we can go to questions from the room. Okay. Let me, maybe if I'd love to ask two questions. Let me, if I may ask one question here right now. So normally I would take the stance on the Gottesman-Knill theorem that stabilizer quantum mechanics is simulable in polynomial time, and I wouldn't care about the exponent. That's what I would usually say. But now that you mentioned this reduction in exponent from 3 to 2, I am somehow intrigued. And so let me just kind of say two things about the stabilizer formalism that I say are facts, but maybe they are wrong, and then you can correct me. But if they are right, then your reduction from degree 3 to degree 2 would really be surprising. And so the way I thought about it is as follows. If we don't care about the signs in the stabilizer formalism, just update Pauli observables up to sign, then we are quadratic. That's the easier part in the stabilizer formalism, just kind of to follow observables up to sign. And the difficult thing is the sign. It is the sign, following the signs in the stabilizer formalism. That's the harder part, and that introduces this cubic scaling. Would you agree with that or not?
Yeah, I mean that sounds right.
You have stabilizer people here in the room? Okay, no objection. But then you have to deal with those signs too. And how can you be faster?
Well, so you initially do a cubic amount of work. Okay, so that's the part that part is almost invisible because there's this exponential term.
Yeah.
Right. So this doesn't sort of imply that there's a quadratic stabilizer simulator here. It's just that the amount of work that you have to do per summoned here is quadratic. And the reason for that is that rather than having to do the same amount of work on every single summon. So if you decompose first and then do Gottesman-Knill and all of the individual ones, then indeed you have to do cubic work on all of these individual ones. Here you're doing the same thing, and it's applying to many different ones. So you're sort of doing the work before you decompose. So somehow you put the cubicness kind of before the exponential part of the algorithm.
Okay, good. Thank you. That's thank you very much. It gives me some idea.
I also have a question. I wonder if there are some circuits and curve, right?
Yeah.
I wonder if there are some families of circuits which are like non-Clifford but still fully simulable in like certain amount of time. Like, have you come up on such families, and if so, what are they?
Sorry, I missed a few words in the question. Could you say it again? I don't know where the microphone is in that room, but
Yeah. So I wonder.
Much better. Yes.
Yeah, I wondered if you come up across some like families of structured circuits that so that you can simulate them like fast for any size that are non-Clifford. And if so, what kind of circuits are they?
Well, I guess the short answer is no. We couldn't find some non-Clifford family, which is kind of simulable to 100% success rate. In the case of the hidden shift circuits, we have actually never made circuits big enough that we haven't been able to simulate at least one. So we're not successful anymore, but it seems like the largest circuits we try, as big as we try, we do find efficiently simulable ones in there, because there's some randomness. We do find efficiently simulable ones in there. So you could say that we stopped at 1400 T-gates just because this was really big and we got tired. But maybe there is some actual reason that these things can be simulated just to kind of arbitrary size.
Thank you. I also have like a little bit of an oddball question. So there were like these diagrams where so there's unitary, and then some outputs are measured in T basis, and some like just go through and you apply the conjugated unitary. And this kind of structures pop up in data compressions, like autoencoders and things like that. And I mean, probably this is not very related, but still, do you think there's some like data compression angle to look at it?
Not that I can think of really. I mean, another way to see this diagram is also that you've kind of plugged in some. You've prepared a state and you've plugged in some sort of bras into part of the state, and then you're just computing the norm of what you have left. So that's why you get this kind of double picture.
Yeah, thank you.
Michael, you're looking at me. Do you have a question? Okay. I would like to ask a question. So when you are applying the spider rules to simplify the diagram, I think you could just as well use these rules to complicate the diagram. Yeah? So I think there's no a priori forward direction.
That's right. Yeah.
So, I mean, you mentioned some cases where in those hidden shift problems where you kind of the circuit and the conjugate circuit kind of the T gates, they were just matching up and you could eliminate them. So that was easy. But beyond that, do you have rules for simplification that you know how to apply the rules to actually simplify the circuit?
So we have a simplification strategy which always terminates. So there's all of the rules we use do something which kind of obviously makes your diagram smaller, like it deletes a node or something like that. These rules are not confluent. Okay, so this means, if I made a different choice, I might terminate at something different. If I apply these things in a different order, I might terminate at a different simplified thing than if I'd done it a different way. And maybe I can get stuck in local minima and this sort of stuff. So there is some kind of leeway for coming up with better rules. There are also some strategies where you do some sort of backtracking, where you don't get stuck in these kinds of minima.
Good, thank you very much. Okay, so there's no question in the chat, no hand raised. So I think that ends the question session. So let's thank Aleks again. Very exciting talk.
Okay, thanks for having me.